Hi, it's Kate, and this is the second day of material for Math S-323. Yesterday, we discussed vectors, introduced them, their basic significance in 2- and 3-dimensional space, and their geometric significance, with some operations like addition and scalar multiplication. In this class, we're going to continue to focus on perhaps the most important operation between vectors, which is the dot product. The dot product here is defined as the following. If we have two vectors, x and y, and remember that x and y are written out component by component, just like they are down here. So what we're looking at here is that the dot product is defined as the sum of the products of the components. So we have the first component of x times the first component of y plus the second component of x times the second component of vector y plus the third component of vector x times the third component of vector y all the way down to the nth components multiplied together. And of course you can write that out like this, or you can opt for a nice concise sigma notation, which just tells you that we're summing together a bunch of like and similarly structured terms. We have the ith component of x times the ith component of y, and the first term is going to involve the first components, then the second, the third, the fourth, the fifth, and so on and so forth, all the way up to the nth component. Now, of course, since we will be working mostly in R2 and R3, these sums will only involve 2 terms and 3 terms. It's important to note that the dot product requires 2 vectors in order to compute it, and it produces a scalar. So while we're eating up 2 vectors here, we take in 2 vectors, the value that is churned out on the other side is just a number. It's commutative, so x dotted with y is the same as y dotted with x, which we will prove. And it is distributive with respect to addition. A dotted with b plus c equals a dot b plus a dot c. We'll learn how to prove some of these things in just a moment. In R2 or R3, the dot product of a vector with itself, like if we take x dotted with x, is equal to the square of its length. Now let's take a moment and discuss the length of a vector. Say we have the vector 2, 3. Let's draw that in the plane. Now, of course, like I noted in class, a vector is not defined by its start point. It can begin anywhere. It is an increment of change. But what's important to notice here is that I've lined it up really conveniently so that it begins at the origin and then it ends at the point 2, 3. And in fact, it is the hypotenuse of the right triangle whose sides are 2 and 3. And so if we were trying to compute the length of this vector, what we would do is take the square root of the sum of the squares here. So that's the length of the vector. Note that 2 is the first component in our vector, and 3 is the second component in our vector. So if we wanted to say, in R2, what's the general formula for the length of a vector, it would look more like this. And that's the general length of a vector in R2. It's the sum of the squares of the components. So of course, if we took x, the vector, and dotted it with itself, instead of having x1 times y1, x2 times y2, x3 times y3, and so on and so forth, we'd have x1 times x1, x2 times x2, x3 times x3. It would look something like this. Remember that length really only makes sense as far as our visualization capability in R2 and R3. The length of a vector still exists even when you're in R4, R5, Rn, however high you want to go. But as far as thinking about it as physical length, it only works mentally and makes sense to us physically when we are in R2 or R3. And so take a look here. We have the sum of squares of the components, which is so close to being the length of the vector. It just doesn't have the square root taken of it. And in fact, we can see that the dot product here is the square of this. So that's why we write the dot product of a vector with itself is the square of its length. Now moving on to the next property, if we take the dot product with any standard basis vector e sub I, it's going to extract the corresponding component. Let's do a concrete example of this. Let's use our x up here where we were using 2, 3. And I'm going to dot it with e1, the first standard basis vector in R2. We note that by applying the definition, we get 2 times 1, the product of the first 2 components, plus 3 times 0, which is the product of the second 2 components. And so we're going to just get 2, which was the original first component in the vector x. And this makes sense because e sub I the ith standard basis vector is going to have a 1 in the ith component and zeros everywhere else. So when you take the dot product of that vector with another vector, the only component that's going to get multiplied by anything other than 0 is the ith component. That's really important to note. Taking the dot product with any unit vector is very interesting because it extracts the component of x along A. Let's take a look at exactly what that may look like. The component of x along A means the shared direction that x and A have together. So what happens, I've really carefully drawn A here to sort of resemble the first basis vector because it's easiest to see in this simplified version. But basically what we're looking at is if we dropped an altitude from x that made a perpendicular relationship with A, we're talking about the length of x if we sort of projected its shadow onto A, which I'll draw in yellow here. That's what that means, to say that the dot product extracts the component of x along A. It's the component of x that has the same direction as A. It's really easy to see when A itself looks like a standard basis vector and I just extracted the first component, but this also works if we draw it like this. We quote-unquote drop a perpendicular altitude from the tip of x down to A, like so. That completes the right triangle. And then it shows us the length of the component of x that is in the same direction as A. Note that in this new example that I've drawn, this component actually is longer than A itself, but that's okay. This property, taking the dot product, extracts the component of x along A, the amount that they are pointing in the same direction, doesn't necessarily have to be the same magnitude as A itself. And what's even more interesting, as I noted in the footnote, or margin note, pardon me, on your notes, is that the difference, when you take x and subtract off this, right here, if you took the vector x and subtracted off that vector, you'd be left with something perpendicular to A, something that had no common direction to A. Let's take a look at what that looks like. Note that the first thing I just did was I translated the vector that is x sub A times the vector A. Now let's slow down and think about that for a minute. Remember that when we took the dot product of x and A right here, what we got out was a scalar because we're taking the dot product. What we got out was the length of this little yellow guy right here. It's not a vector, we were just given the side length, and so in order for us to think about a vector whose length is this yellow guy but whose direction is the same as A, that means we need to take A that has length 1 and scale it by this length, which is x sub A. And so that's why in your margin note it says we take the difference between the vector x, this blue guy, and then the vector, which is the scalar xa, times the vector A. Because A, the red guy, who's underneath this yellow part, gives us our direction, and then the actual dot product that we had calculated gave us our appropriate length. And so when we then want to subtract that off, we change the side that the arrow's on, because note that A was pointing in that direction. Now negative xa times A will be pointing in the opposite direction. And we want to connect the start of x to the end of xa times A, and we have this. And what this property is telling us is that, the margin note, pardon me, is telling us is that this green vector is perpendicular to A. It really has no common directional component. They're not even slightly pointing in the same direction. They are exactly orthogonal to each other. How do I know that they're orthogonal? Well, their dot product is 0. Well, I haven't actually written out a proof of why a dot product of 0 between two vectors would indicate orthogonality, but we're about to get to that on the next page when we define the dot product a little bit differently. Let's take a look. Now, from elementary trigonometry, a lot of you remember the law of cosines, which is written as c squared equals a squared plus b squared minus 2ab cosine alpha, where a, b, and c are the lengths of the sides of a triangle, and c is the length of the side that's opposite the angle alpha, and angle alpha is between the two sides whose length are a and b. Let's write this down in a new way. We're going to use vectors. We're going to consider the triangle whose side lies along the vectors x, and x has length a, so let's draw that first. Then there's y that has side length b. And then our third remaining side that's missing from this triangle is actually x minus y. And you do need to take a little check in your mind to make sure which side of that green vector the arrow is going to be on. But remember that if y is pointing in this direction, then if we wanted to add on minus y to x, we'd want it to point in this direction, and so x minus y would be pointing like that. So it looks like so. I went ahead and completed labeling the side length c as well as adding the angle measure alpha. So let's take a look here. By the distributive law, we know that if we took this side, x minus y, this vector, and we dotted it with itself, that would be x minus y dotted with x minus y. And we told you guys that the dot product is distributive, so we can use sort of a FOIL type of operation just like we always would. We'd have x dotted with x, right, first, then outside, x dotted with y, inside, minus y dotted with x, but of course this is also minus x dotted with y, so we have minus 2x dotted with y. And then last, which is minus y dotted with minus y, which is just y dot y. And note that here these can be simplified, because remember that when we take a vector and we dot it with itself, we get the square of its length. So when we convert this statement, just foiling this side length dotted with itself, we end up with, well, this is the square of the length of x minus y. And remember the side x minus y had length c. This is the square of the side of length of x, so that's side length a, so that's a squared. This is the square of the length of the vector y, so this is b squared, and then we're left over with this weird minus 2x dotted with y. Well, let's compare that to the law of cosines. Let's scroll down a little bit. The law of cosines says that the side length there, where we have c squared, is equal to a squared plus b squared times 2ab cosine alpha. So lo and behold, if we equate these two, we say, hey, c squared is equal to a squared plus b squared minus 2 times x dot y. And c squared is equal to a squared plus b squared minus 2ab cosine alpha. If we equate those two sides, the a squareds will cancel out, the b squareds will cancel out, the factor of minus 2 will cancel out, and we are left with the fact that we are told that x dotted with y is going to be equal to ab cosine alpha. Remember that a is the length of the vector x, b is the length of the vector y, and cosine alpha, that remains the same. So we have this new definition of the dot product from relating trigonometric properties, the law of cosines, to the fact that we know the dot product, when we take a vector and dot it with itself, we get the square of its length. So just by using those two facts and the distributivity of the dot product, which we will prove, we found a new way of expressing the dot product. So we have two ways. The one at the very, very beginning was the sum of the products of the components, and now this one is saying that x dotted with y is equal to the length of x times the length of y times cosine alpha, where alpha is the angle between the two vectors. That's crazy. For a long, long time, I just took it on good faith that the two were equal. I couldn't imagine why taking the products of the components was at all the same as taking the length of both, multiplying them together and multiplying by cosine alpha. But I thought, you know, for this particular class, it's good for teachers to know how the two are related. So that's what we're going to do next. We're going to find our path from one definition to the other and show to ourselves that they are, in fact, equal. Let's take a look. All right, here we go. Our goal is to show that these two different ways of describing the dot product, the length of x times the length of y times cosine alpha, where alpha is the angle between them, and the sum of the products of the components, are actually equal. And this is what I kind of affectionately refer to as a toolbox proof, where you make a ton of observations about the dot product first. They seem sort of unrelated, but you build up an understanding of how the dot product works, and then the proof itself is only a few short lines. So the first thing that you want to take a look at is that we want to express x and y as the sum of multiples of standard basis vectors. Now remember that x and y can be written like this. And just as we talked about at the very end of class yesterday, those are actually coefficients of the standard basis vectors. That actually means x1 times e1 plus x2 times e2 all the way down to xn times en. I'm even going to write that more succinctly using sigma notation, because every single one of these terms is the ith component of x times the ith standard basis vector, and we start at I equals 1 and we go up to I equals n. You can write y similarly, just like this. So that's our first observation. Now, I actually didn't put enough space in the notes, but there's an important observation where we want to show that even this definition of the dot product observes the distributive property. Let's take a look at what that looks like. Alright, so here's our setup. Here are the vectors x and y, and here's alpha, the angle between those vectors. And we know the dot product definition is that it's the magnitude of x times the magnitude of y times cosine alpha. So let's take a look. When we drop this altitude down and we create this right triangle, visually speaking, let's take a look at what happens when we're looking at the magnitude of y times cosine alpha. Well, cosine, of course, is adjacent over hypotenuse, but when we multiply a cosine by the length of the hypotenuse, we're left with the length of the adjacent side. So that's yellow side here, this bottom, the base of the right triangle in our picture, is the length of y times cosine alpha. Now, of course, it gets multiplied by the length of x, but let's picture something with an even different vector. So maybe x and z. Here we have x and a new vector z. Now the dot product between x and z would be the length of x times the length of z times cosine, and I've called this angle here beta because it's not the same as the angle between x and y. And again, when we drop that altitude down from z and we take a look at, oh hey, we have this right triangle here, here's beta. If we took the length of z times cosine beta, we'd have the length of the base of that right triangle. So far we've deduced that the dot product of x and y is going to be the length of the yellow part times the length of x, the blue vector. And then down here, the length of this yellow part times the length of this blue vector when we're talking about the dot product between x and z. Now let's take a look at what the dot product would be between x and the sum of y and z. Now here we are picturing x, here's y, and here's z, so here's y plus z. We now have x and a new angle between x and y plus z, which I'm going to call gamma. And so the dot product between x and the sum of y plus z would be the length of x times the length of y plus z times cosine gamma. And of course, just like in these examples above, if we dropped an altitude down here and looked at this right triangle whose base was along x, whose altitude was here, the height there, and the hypotenuse was y plus z, we'd find that the length of y plus z times cosine gamma would give us this. So that turquoise part is the length of y plus z times cosine gamma. Now what's interesting though is that part of it, this turquoise part, is made up of the sum of the two other yellow parts that we had drawn in these diagrams up here, right? Up until here is the length of the yellow part where we had length of y times cosine alpha, and then the remainder of this out until here, try to use a different color, is the length of what was the yellow part here when we did z cosine beta. And so together, this length plus this length is equal to y plus z cosine gamma. And so we can see that if we were taking the length of the yellow times the length of x, the length of the yellow here times the length of x, that's the same thing as taking the length of the sum of those two pieces, which is now the turquoise part, times the length of x. And so we have a distributive property in this definition of the dot product. That's probably the hardest conceptual part of this entire thing, and I really wanted to be rigorous and make sure we hit on every single point. Let's take a look at what is E sub I dotted with E sub I. According to this definition, well, let's write it down. Well, it would be the length of the first vector times the length of the second times cosine alpha, where alpha is the angle between them. If we're talking about the same standard basis vector, well, standard basis vectors always have length 1, right? They always have one component where the component is 1 and all the other components are 0. So we have, this is 1 right here. This is length 1. Of course, e sub I is also length 1. Cosine alpha between two identical vectors, well, the angle between two identical vectors is just going to be 0. So cosine of that is 1. So we have 1 times 1 times 1, which is just 1. What's interesting to note is, what if we had two different standard basis vectors? What about e sub I dotted with e sub j, where I and j are not the same number? You can think about e1 dotted with e2 in R2. Well, they both have length 1, so we have the length of e sub I is 1, the length of e sub j is 1, and cosine alpha between standard basis vectors, alpha is going to be pi over 2. So cosine of pi over 2 is 0. So we have 1 times 0, which gives us 0. All right, our very last observation before we sort of blitz through this, you'll be surprised at how easily all of this comes together once we have these tools in place, is what is x dotted with e sub I, where I is a standard basis vector? Well, let's take a look. Now, I've drawn a very similar diagram. I picked E1 as just a concrete example here, where I have a vector x, and then I also have the first standard basis vector. And when we take a look at this, we know that the way to compute the dot product will be to take the length of x, the length of the first standard basis vector, and cosine alpha, where alpha is the angle between the two. And of course, taking the length of x times cosine alpha is just going to give us the length of the yellow piece of this, or the base of the right triangle. What's particularly interesting, though, is that since this is in the direction of the standard basis vector, the first standard basis vector, this is actually the component of x in the first position. So this is the first component of x, right? This is telling you how much the vector x moves to the right or to the left. And so in general, x dotted with e sub I is going to extract the ith component of x. All right, we have all our tools. We know that the dot product using the geometric definition, the magnitude of x times the magnitude of y times cosine alpha, is distributive. We know that we can write x as a sum of scalar multiples of standard basis vectors. We know that standard basis vectors dotted with each other that are the same are 1. We know that different standard basis vectors dotted with each other is 0. We know that a vector dotted with a standard basis vector extracts the ith component. And we're going to put all these skills together in a nice, clean proof. All right, the very first thing I want to say is that, hey, x dotted with y. Let's express y as a sum of standard basis vectors. All right, I've rewritten y as a sum of standard basis vectors just like we did at the very beginning. Now, note that the dot product is distributive. So I could say this is the dot product of x with a sum of standard basis vectors, or I could say it's a sum of many different dot products and different dot products. That's tantamount to bringing x inside the sigma notation. It's also worth noting that we can actually pull out this scalar multiple here, this y sub I. Why can we do that? Is the dot product something where you can factor out a scalar? Let's think about that. Are these two facts true, the way I've written it up here? So I started with x dotted with cy. Is that the same as c times x dotted with y? So I just applied the definition of the dot product to either side. It sort of hinges on whether cy is equal to c times y, and we have cosine alpha here and cosine alpha here. And you may be saying, no, it's definitely not, because this is always positive, but c could be negative. That's very good. But remember that if c was negative, it would change the direction of y, and it would also change the sign of cosine. So what I'm saying is that if c was a negative number, well, first, let's point out that if c is positive, these two statements are equivalent. Everyone agree? Great, right? Alpha has not changed. Y has just gotten longer. This term, c, the length of cy is the same as c times the length of y. That's great if c is positive. But if c is negative, note that the angle between x and cy is not the same as the angle between x and y. That's the key. If x is negative, you are going to have a value for alpha on the left-hand side, that multiplies the cosine value on the right-hand side by -1. We'll go through this in more detail in class, but it does hold even if c is negative. On this side, the negative term will come from c. On this side, the negative term will come from the value of cosine alpha. So what we can do in this next step is we can pull out y sub I as a scalar. And then, oh, look at that. We're left with x dotted with e sub I, which up here we said that x dotted with e sub I is going to extract the ith component of x. Let's simplify that. Lo and behold, we have the sum of products of the components of two vectors. We can rewrite it to exactly match the other definition, and then we're done. I'll put the last justification here, but that's it. We started with only the magnitude times cosine alpha, where alpha is the angle between them definition, and we got to the sum of the products of the components. A miracle! Huzzah! Let's take a look at how to prove some things about the dot product. Earlier we stated that the dot product was commutative. So let's take a look at how to prove that. Well, first we start with the definition of the dot product, and I'm going to do the sums of the products of the components. You sort of have to think about which definition, which computational definition is going to help you the most in the proof that you're doing, and a lot of the time it's the sum of the products of the components. I've written out the dot product and I've just written definition next to it. That's great. And remember that the components of these vectors are just members of the underlying field of real numbers. And so multiplication in this field is commutative. I can swap their order. So I wrote here that we have the axiom of the underlying field of real numbers and that multiplication commutes. And of course, this is just the definition of y dotted with x by definition of the dot product. And we're done. And a lot of the proofs involving the dot product follow this exact same format. You apply the definition, you exploit some underlying field axiom, and then you apply the definition again to untranslate out of this component by component definition. Let's take a look at number 2. Show that if the length of x is greater than the length of y, then the length of x minus y is greater than or equal to the length of x minus the length of y. Note that if the length of x is less than y, this would just be really trivially true because the right-hand side would be negative. So this is the more challenging version where the length of x is actually greater than the length of y. Let's take a look at how we can manipulate the left-hand side and right-hand side. And so what we're going to do is we're going to use the relationship that the dot product has with the length of a vector. Now if you recall back to the beginning of this, that means that the square of the length is equal to a vector dotted with itself. So let's take a look at the left-hand side. I'm actually going to square the left-hand side, and I'm going to set that equal to the vector x minus y dotted with itself. That's just the definition of the dot product. That's fine. Now remember that the dot product's distributive, so we can sort of FOIL this out. And then we note that we have a lot of instances where we have vectors dotted with themselves, and so those are the squares of the lengths of those vectors. Let's rewrite it one more time. So this is the rewritten square of the left-hand side of this. Let's try to rewrite the right-hand side in the same way. We rewrote the square of the left-hand side. Let's rewrite the square of the right-hand side. Alright, so there's the square of the right-hand side, and we basically want to ask the question, is the following statement true? Is this, the rewritten square of the left-hand side, greater than or equal to this, the rewritten square of the right-hand side? Well, we need to investigate more. It's clear that by algebraic manipulation, we can actually cancel out a lot of terms. We can say, oh, there's a length of x squared on both sides, so we can cancel this and this. There's a length of y squared on both sides, so we can cancel this and this. We're left with a factor of -2 on both sides, so let's divide by -2, but remember that's going to switch the direction of the inequality. So now we're left with the question, is this true? Is x dotted with y less than or equal to the length of x times the length of y? Now, of course, let's use a definition of the dot product. This looks so close to being the length of x times the length of y times cosine alpha. So let's put that to use on the left-hand side. Here we have a much clearer question. Is the length of x times the length of y times cosine alpha less than or equal to the length of x times the length of y, pardon me? Well, yes, it definitely is. This is certainly a true statement, and that's because cosine alpha is at most 1. When it's less than 1, the left-hand side will be less than the right-hand side, and certainly when it's negative, the left-hand side is going to be less than the right-hand side, which will always be positive. So yes, this is true. This is not a proof. This is more of a show us that the following is true. So this is not a rigorous proof. That's why there aren't all these justifications on the side. There are a lot of famous inequalities in mathematics that come up about the dot product. The first of which is the Cauchy-Schwarz inequality that says that the absolute value of the dot product is less than or equal to the length of v times the length of w. And people always want to jump in and say, well, that's obviously true because of that v times w times cosine alpha thing. But note that when we are in Rn, angle measure no longer makes sense. When we're in R2, Euclidean space, like two-dimensional planes, and R3, which is three-dimensional space, we can figure out the angle between vectors. But once we get into R4, we don't know how cosine behaves. We don't know how angles behave. And so we can't just use the definition of the dot product here. And I've left a proof here for you to read through, which is very nice. I'll go over it in class. But it's pretty illustrative, and it shows you exactly why this relationship is true. All it does is it takes a vector and dots it with itself, and you know that the square, that's going to give you the square of the length of a vector, and which is always going to be greater than 0. So that's the only neat choice. That's the only jumping off point that seems sort of strange or a strange idea, but the rest of it is just algebra, and that's it. If you have any questions, don't hesitate to ask. But of course, we are sticking in nice 2- and 3-dimensional space. Let's take a look at this sample problem, which asks us, okay, we have two vectors here. Let's determine the angle between v1 and v2. Well, we know that the dot product gives us one way to find the angle because of this definition. So here we are. We need to figure out the lengths of the vectors v1 and v2. And we do that by taking the square root of the sum of the squares of the components. So the square root of 4 squared plus 1 squared plus 1 squared is the square root of 18, which is just fancy for 3 root 2. So I'm going to write up here next to it that the length of v1 is 3 root 2. And the square root of the sum of the squares of the components of v2, which is negative 2 squared plus 2 squared plus 1, is 9. So square root of 9 is 3. So we're going to use that on the right-hand side of this. And I just grouped them in parentheses so you could sort of visually think, okay, the first thing is the length of v1, the second thing is the length of v2. And on the left-hand side, I'm going to exploit the other definition of the dot product, which is the product of the sums of the products of the various components. So we have negative 4 times negative 2, plus 1 times 2, plus 1 times negative 1, which happens to be 9. When we solve for cosine alpha, we actually get 1 over the square root of 2, or root 2 over 2, I should say. And so what angle measure has cosine of root 2 over 2? That's going to be pi over 4. Now here's a good problem. Determine the area of the parallelogram spanned by v1 and v2. Well, since the dot product of v1 and v2 is positive, I know that the angle between them is an acute angle. So that's kind of a sigh of relief because I can just really draw these quite nicely. Even though they live in R3, I'm going to visualize it like this. And so what we're looking for is the parallelogram that is created when we sort of fill in everything else. Well, the area of a parallelogram is the length of the base times its height. We already have a base here. That's going to be like our v1, and then we need this height here. So we need to use the dot product to sort of fiddle around with it. All right, so we know the definition of the dot product is v1 dot v2 equals the magnitude of v1 times the magnitude of v2 times cosine alpha, where alpha is the angle between these. And in particular, what we're really interested in, because it's very nice to see this right triangle, and in fact, we can use the Pythagorean theorem on it. We know that its hypotenuse is the length of v2, and we know that we can actually get the base here, right? Because that means that we've discussed this when we were doing the dot product earlier, that cosine times the length of v2 is going to give us the length of this base here, the adjacent side. So let's solve for cosine times the length of v2. And if we have the length of this side and the length of this side, we can use the Pythagorean theorem to get the length of that side. So what we're using the dot product to do on this side is using it to compute this little tiny base of the right triangle. We did a lot of the computation for this in the first part. We know that v1 dotted with v2 is 9. We also know that the length of v1 is 3 root 2. And so we know now that this yellow guy is 9 over 3 root 2, or 3 over root 2. So we know the two sides of a right triangle. We can use that to deduce the third to find the height. So we know that. So I just used the Pythagorean theorem to say that the height of this right triangle squared plus the base squared, which is 3 over root 2 squared, equals the square of the hypotenuse. And the length that v2 was 3, so the hypotenuse squared was 9. When we solve for h, we end up with 3 over root 2. And so now we have the height, and we also have the length of the base, because v1 itself was 3 times root 2. So the area here is going to be the length of v1, the length of the base of the parallelogram, 3 times root 2, times the height, which is 3 over root 2. The root 2's will divide out, and we're left with just 9. And that's that. Last but not least, we have the triangle inequality. If we have two vectors, x and y, that are lined up so that they are head to tail, we have the third side that coincides with the vector x plus y, right? We start at the beginning of x and we go all the way to the end of y. And so the triangle inequality, which we use all the time in teaching geometry, is saying that the lengths of any two sides is always greater. The sum of those lengths is always greater than the third and final side. So we say that the length of the side x plus y is less than or equal to the length of x plus the length of y. And there's actually a quick proof of this using the dot product. We take the square of the length of x plus y. We notice that the square of the length is equal to that vector dotted with itself. We use the distributive property for the dot product. We have x plus y dotted with x plus y dotted with y, and then we apply Cauchy-Schwarz, which was the previous proof that was on page, let's see here, 15, I believe, or 16 of your handout. And so what that's saying is that the dot product of any two vectors is less than or equal to the product of the magnitudes of those two vectors. So let's scroll down here. So that absolutely leaves us with, okay, this is going to be less than, this term itself is going to be less than or equal to the length of x plus y times the length of x. This term is going to be less than or equal to the length of x plus y times the length of y. And so this whole side will be less than or equal to the length of x plus y times the length of x plus the length of x plus y times the length of y. And note that there's a factor of x plus y in every single term. And that's a positive number, so we can divide out. It's going to be non-zero. And so what's great about that is we are left, we don't have to worry about dividing by 0, we don't have to worry about swapping the inequality. We're left with the fact that, oh, the side, the green side, length of x plus y, is going to be less than or equal to the length of x plus the length of y. And that's it. In your problems that you'll be doing in group work as well as on your homework, you can certainly expect to see something that involves a proof using vectors and using the dot product especially, but also proving something about the dot product, and last but not least, sort of manipulating angles between vectors or computing angles between vectors using the dot product. As always, if you have any questions, don't hesitate to email.